Good morning, everybody. So I hope you had a very good spring break and enjoyed your spring break. Thank you, Del. Thank you, Fox. Thank you, Corey. So thank you, Ronald. You have any question concerning previous topics? Thank you, Marco. Any comment, any question about uh, complex topics in complex that we have covered so far? Okay, I don't see any question. Um, Today I just decided, I hope you had a good chance to review the material during this spring break. But what I'm going to do today is uh, a quick review of chapter 16, all right? 16.12 and eventually 16.3, which is taught about a residue theorem. So um, this chapter started with uh, the, this Laurent series, okay? Uh, and then we talked about, in Laurent series, the function is, oh my goodness, let me change the camera. So um, the function is analytic. If the function is analytic in uh, alpha, so we are going to have a Taylor series. Doesn't have any negative exponent of z minus alpha, right? But if and we know what ANs are, right? ANs are these. But if the function, this alpha, is not a good point, is let's say singularity point, then instead of Taylor series, we are going to have uh, this Laurent series, all right? Well, the singularities, the bad points, we decided to have two main categories of those singularities. One is isolated singularities, all right? When we say isolated singularities, in a neighborhood of that alpha, everything is fine, except that alpha itself, all right, is function doesn't have derivative. Those are called isolated singularities, and here I gave you examples, the zeros of this denominator. Those are the only bad points of this function, all right? Other than these, the function is perfectly fine. Then we have non-isolated singularities, and that basically goes with very weird functions, including the logarithm. In logarithm, we know that derivative doesn't exist in the negative direction of x-axis. So it is not just at one point, but any neighborhood of that point you consider, there are infinitely many other points that derivative doesn't exist, okay? Those type of points are called non-isolated singularities. Okay, well, we basically are going to talk about isolated singularities, okay? So isolated singularities, as I mentioned, the function is perfectly fine in this neighborhood, except at alpha itself, right? And we usually denote it by this. We exclude alpha, right? But the isolated singularities themselves, we classified them and we made them into three categories. One was a removable singularity, one was a pole, one was a simple singularities. I'll talk about that later. But here is the Laurent series. So the function is perfectly fine at a neighborhood of alpha, right? Except at alpha. Alpha is a bad point. Other than that, so the function is fine. In Taylor series, the function is also good at this alpha, but in Laurent series, the function is not good at this alpha. And we do have a series like this one, but in this case, we are going to have negative exponent of z minus that alpha, right? That bad point. Yeah, maybe I should, instead of alpha this time, say z naught. Look, well, the coefficients are right here, exactly the same coefficients that we had in Taylor series, except here n can be an integer, n can be negative, right? Well, one beautiful observation here is what happens if n is -1? If n is -1, denominator will be this to the 0, exponent is 0, and that's 1. So it will be just the integral of f of s ds. And that is always what we are after, integral of f of s ds or f of z dz over a circle, right? So in Laurent series becomes extremely important because we need this coefficient. This coefficient will give us the integral of f of z dz, right? This coefficient is called residue of the function at that particular point, okay? And we denote it by this, residue of f of z at that singularity z0. And as a result of this observation, integral of f of z dz over a closed curve that contains that z naught is 2 pi I, this coefficient of that 1 over z minus z naught. All right, okay. That's a beautiful observation. We will use this a lot. But when you look at the Laurent series, from this constant, then all the positive powers of z minus z naught, we don't have any problem with this part. This is the analytic part of the function, and that is exactly what we call it. We call it analytic part of that Laurent series. But the portion that contains z minus z naught in denominators, which is negative exponent of z minus z naught, that is called principal part of that Laurent series. Okay, or the function. Based on this principal part, we classify the isolated singularities, all right? The isolated singularities. Okay. Uh, so, uh, starting with the removable singularities, and that is when, uh, after writing the Laurent series, you don't have any principal part, no negative exponents of z minus z naught, right? That is called removable singularity. And I gave you this example, sine z over z. Then we have a pole of order n. And pole of order n is when you look at the principal part, you have finite number of terms, right? The largest exponent, the largest exponent of z minus z naught in denominator, that is what we call order of the pole. So in this case, we call z naught a pole of order n. And if everything, we only have this term here, we call it simple pole, right? Simple pole. Anyway, the characterization of pole of order n is that if you factor the largest denominator, right, here, everything that we have in this curly bracket is analytic. So the function has a pole of order n if and only if the function can be written in this fashion, where numerator is analytic and is not zero at that point. Okay, that is a pole of order n. All right. So the third type of isolated singularities is what we called essential singularities. And that is when you write the Laurent series of the function, and the essential singularity is when the principal part has infinitely many terms. An example is right here. If we write the expansion, Laurent expansion, you get this one, all right? So this is the principal part where all the z's are in denominator. How many terms do we have? Infinitely many. So this is when we call essential singularity. All right. Of course, one of the questions that, or one of the, questions that we will get, is this: when you have a singularity, you're supposed to figure out what kind of singularity is that. Is it a pole, removable, or essential singularities? All right. So that's one of the questions that you are going to deal with, including in your next test. I gave you a bunch of examples. Here is one. We have a bad point, the singularity at 0. So when you write the Laurent series, you get this one, okay? So it is a pole of order 3, a pole of order 3. And then I talked about the zeros of a function and the correlation between zeros and poles. first, of course, I introduced the definition of what do we mean by a zero of order n. Oh, this Brandon is asking why it is pole of order 3, because after you write the Laurent series, this is what you get. Now, in this expansion, this is the analytic part that we are fine with it. So you look at those terms that z is in denominator. And the largest degree is the order of the pole. So the largest degree is 3. So it is pole of order 3. Well, of course, you could have said it right here, right? Just by looking at the function. Because numerator is fine and numerator is not 0 at 0, cosine of 0 is 1. We could have said it right here. But in general, it's better to write the Laurent series and then make the judgment of what kind of pole it is. Yes, it is. That's you're right, Brandon. It's always the larger degree of denominator. Okay, good. So talking about zeros, we call it a zero of order n if not only the function is 0, but its derivative, its second derivative, up to n minus 1's derivative, all of them also be 0. If this is the case, we say this point is a 0 of order n. Well, if it is 0 of order n and the function is, let's say, analytic at that point, we can write the Taylor series. And in Taylor series, if these guys are 0, we replace them by 0. The first term will be this one, and second term, and so forth. If we factor z minus z naught to the n, in this curly bracket, everything is fine. It's a power series, right? And we are okay with it. This is an analytic function. So 0 of order n, another characterization of 0 of order n is this, that you can factor z minus 0 to the n. If that's the case, it is 0 of order n. But remember, when you factor it, this guy should be analytic and not 0. If this guy be 0 at this point, that means, oh, well, we have another 0 in the structure of this. So this guy has got to be 0. So that is the 0 of a function. And there is a beautiful correlation between zeros and poles. And the correlation or the relationship between these two is right here. This function is, when it is a nice function here, has 0 of order n if and only if its reciprocal get a pole of order n, or vice versa. This one has a pole of order n if its reciprocal has a 0 of order n. Okay, all right. Here's an example. I want to see, of course, this is 0 when you let z be 0, this will be 0. But the question is, what is the order of this 0? You go ahead and write the power series of zq, sine zq, which is this one, multiplied by z squared. Okay, you get this one. Now, if you factor z to the fifth, in this curly bracket, this is no longer 0 at 0. It is 1 at when you replace in the curly bracket. When you replace z by 0, you get 1. So this is what we get. All right. So 0 is a 0 of order 5. The order of this one, the 0, is 5. Okay. Any comment, any question? It's just a quick review of what I talked about in the week before your spring break. Good. Well, here is another example, just to make sure that we understand what's going on. Oh, look at this function. This has a singularity. Usually singularities are the zeros of denominators. So yes, all right. So here we have a singularity, 0. The question is, what is the order of, it's the pole, right? What is the order of this pole? And writing the Laurent series is the best approach. So here is e to the z minus 1. In this curly bracket is e to the z minus 1. You divide by z cubed. This is what you get. All right. Now, the largest degree of z in denominator is 2. So z equals 0 is a pole of order 2. Is a pole of order 2. And remember, when we write the Laurent series, the coefficient of 1 over z is called residue. And we need this one because the integral of this function around unit circle, let's say, it will be residue times 2 pi I. All right. Okay, good. Here's another function. This time we want to find the zeros, order of zeros, all right? Again, if you factor 0, you get e to the z minus 1, and here is e to the z minus 1. So you factor z, get z squared, okay? So in this case, z equals 0 makes the function 0, of course. But the question is, what is the order of this 0? In this case, the order is 2. The order of this 0 is 2. Okay? So, just writing the Laurent series will help us to classify the singularities. And when I say classify singularities, basically, I'm talking about isolated singularities, whether it is removable or it is a pole, or it is an essential singularity. All right, that's also, okay, good. Also, it will help us writing the Laurent series or Taylor series will help us to find the order of zeros. The order of zeros, okay? Any comment, any questions so far? The image is a little bit blur. Let's see if I can make the image sharper. Yeah, it's better now. Okay, good. So far, so good. I guess I gave you enough examples, but here comes the um, residue theorem. So then we talked about Cauchy's theorem, and this is also good because we are also having a review of Cauchy theorem as well. If the function is analytic here, has no bad point inside this closed curve, no bad point, and it's just simply connected. There's no hole in here. The Cauchy theorem says the integral is zero. Done. How about if we have a bunch of singularities, a bunch of bad points? Again, Cauchy theorem says integral over this outer boundary, right, is equal to sum of the integral over these little boundaries. We usually isolate those singularities. Then the integral over the whole thing will be equal to the integral over these. All right, that's just remember that Cauchy theorem. When it comes to integrating over each one of these, we use that residue theorem because the Laurent series says this is the expansion, this is an, and when n is -1, a -1 is right here. And this is what we need. Okay? So, putting these together, that's residue theorem. So, we will put these two together. So, the coefficient of this guy, which is called residue at that point, and this is the notation, an integral over that little circle centered that singularity is going to be 2 pi I residue at that point. Okay? So, combination of these two, the Cauchy's theorem and this one, tells us that, look, okay, here is what we call residue theorem. Remember, Cauchy theorem says integral over this whole big outer boundary will be equal to integral over these, sum of those, adding these, okay? Now, what is the advantage? The advantage is when you are doing integral over this one, there is only one bad point inside. One bad point on. And now the integral over this one, based on the Laurent series, will be 2 pi I residue at that point. So this is called residue theorem. All right. Any question about residue theorem before I give you some examples? Here comes the examples. First, of course, now the question is, how do we find that residue? Well, the very natural way to write the residue is writing Laurent series, with center being this point, and the coefficient of this guy is that residue. That's a very natural way of doing it. But there are some special cases. Those special cases is what I call simple pole. When the function looks like this, and I need this B, okay? It's a simple pole. The order of pole is 1. Well, in this case, if I multiply by z minus z naught, the whole thing, I will get B, and the rest will be multiplied by z minus z naught. As z approaches z naught, this part will be 0, and you get B. So, if it is a simple pole, one way to compute residue is this. You multiply by z minus z naught and take limit. There is another way of doing it, and that's when you are dealing with a quotient. Suppose z naught 0 is a simple pole here, which means denominator is 0 at that point. Okay. When you multiply by z minus z naught, you get this. Now, as you take limit as z approaches z naught, denominator here will be derivative of denominator evaluated at z. So here is the second way, the second approach, the second technique of finding residue at simple poles. Remember, simple poles, all right? Simple. So for simple poles, I would say we have 3 different ways of doing it. One, which works for any pole, is writing Laurent series. 2, I call it 2A. 3, the third method, I call it 2B, which is this one. Numerator divided by derivative of denominator. You evaluate that at z naught. That is the residue, okay? Now, what if it is a pole of order n? It is not a simple pole. So, well, last time I told you, for example, a pole of order 2 looks like this, okay? When you write the Laurent series centered at z naught, you get this. And the highest degree of denominator is 2. This is a pole of order 2. Now this time we will multiply by z minus z naught square to get this. But remember, I need this one. I need coefficient of this guy. I need B. If I multiply by this, here is a constant. B will be multiplied by this. But if I take derivative now, this will be 0, and derivative of this guy will be b. So I'll have b. All right? So when you have a pole of order 2, this is what you do. You multiply by z minus z naught squared and take derivative. After taking derivative, take limit as z approaches z naught. Well, before spring break, I told you, please go ahead and do this process for n equal 3. And I trust that you did. In general, when you have pole of order n, this is what you do. You multiply by z minus z naught to the n as pole of order n, okay? And you need to take derivative n minus 1 times to get to that coefficient of 1 over z minus z naught, right? So this is what the formula is for the pole of order n, okay? Any comment, any question? All right, I don't see any question. Let's continue. Here comes some examples. Look at this function. I'm going to this. And zeros of denominator, of course, are singularities, right? Bad points. But always we use shortcut. We already know that e to the w has this expansion. Now, in our case, w is 1 over z. So replace w by 1 over z. This is what you get. Oh, 2 over z. All right, 2 over z. So the Laurent series, oh, by the way, this is an essential singularity. Why it is essential singularity? Because this is the principal part, and in principal part, we have infinitely many terms. We have infinitely many terms where z is in denominator. But among all of this, we need this part, this one. The coefficient of 1 over z is 2, and that is the residue. That is the residual function at 0, okay? At that singularity. Here's another example, finding residue of this function at its singularity, and the back point of this function is 0. But, you know, this is the expansion of sine w. I replaced w by 1 over z. Now you multiply by z to the 4. You get this. Well, this is the analytic part. And from this point on, here you have the principal part. You have infinitely many terms in the principal part, okay? When you have infinitely many parts, infinitely many terms, That is called essential singularities. But, okay, we need the coefficient of 1 over z. Why? Because that is going to give us the residue. Why residue is important? Well, residue is important because by that residue theorem, it will give us the value of integral. Okay, suppose here is the function, and you want to find the integral of suppose you want to find the integral of z to the 4 sine of 1 over z. The only bad point is z equals 0, dz. There, I remember in complex, we always integrate over a curve. So let's say the unit circle. Oh, we would like to find the value of this one. Based on the residue theorem and the Laurent series coefficient, this is equal to 2 pi I residue of the function at this z equals 0, its singularity. Remember, singularity is inside at 0. So we already found that based on this Laurent series, we found that the residue is 1 over 5 factorial. All right, the coefficient of 1 over c. As soon as you have this, then you say, all right, the value of this integral is 2 pi I over 5 factorial. This is how important residue is. Okay. Did you get it, Del? That is how important finding residue is. Because residue, after finding residue, will give us the value of integral. But in that example, I'm just finding residue. Of course, we can combine this with integration, all right? We can combine this with integration. But for the time being, I'm practicing the calculation of residues. Here's another example. 3z plus 2 sine z. Oh, of course, 0 of denominator is a bad point, a singularity. But it is simple pole. It is a simple pole. How do we find the residue here? Because it is simple pole, we multiply by z and take limit. A limit of this one is 1, here you get 2, okay? I'm using that 2a. So just used based on notation that I gave you earlier. If you are writing, you're taking notes, I used method 2a. Because it is a simple pole and I could do that. Here's another example. So z equals 0 makes denominator 0. Oh, there might be some others, but at the moment, I would like to find the residue at 0, which is a simple pole, right? It's a simple pole. Because it is a simple pole, I can use either 2A or 2B. In this case, I have used 2B, the technique that I explained earlier, 2B, which is numerator divided by derivative of denominator, evaluated at that bad point. So the residue in this case is negative 1/4. All right. Any question about this one? Finding residues are extremely important because it is going to give us the value of an integral. Here is an integral. I want to find the value of this integral over this circle centered at 1, radius 2. Oh, centered at 1 is here, radius 2. This is the circle. So this is the circle, right? Centered at 1. Here is the x-axis, y-axis. Well, there are 3 bad points, 3 singularities. Z equals 0, z equal 1, and z equal 2. We have 3 singularities. Using Cauchy theorem, the integral over this one will be equal to integral over this little ones. Some of those, okay? Now, why do I want integral over these little ones? Because there will be only one singularity inside, and the integral over this one will be 2 pi I residue at 0. Integral over this 2 pi I residue at 1. Here, 2 pi I residue at 2, and you add them. So 2 pi I residue as 0, residue as 1, residue at 2 of that function. But thanks God, all three of them are simple poles. Right? The degree is 1, the simple pole. When it is a simple pole, I can use that technique 2B, which is numerator, whatever numerator, divided by derivative of denominator. And you evaluate at 0, 1, 2, all right, and put in here. And if you do that, well, it just happens that we get 0, okay? But in this case, it is 0, but it didn't have to be 0. It could be a number or something. For this particular function, it happened that the integral was 0. Okay? So this is why residue is important. And residue theorem is important because it will give us the value of integral. So the value of this integral over this uh, circle after applying residue theorem is 0. Okay? Is 0. Any comment? Any question? Oh, let's see if I have another example for you, because it's such an important topic. Okay, let's do this one. I want to integrate tangent z over this circle centered at 0, radius 2, over this. Yeah, in this case, I used 2b. I could have used 2a, all right? I could have also used 2a. As a matter of practicing, as a matter of demonstrating that how you can use 2a or 2b, I gave you two different examples. In one of them, I used 2a. In this one, in the previous one, I used 2b, okay? Right. If it is a simple pole, or remember Del Dodson, if it is a simple pole, you can use 2a or 2b, okay? If it is a pole of order 2, then you cannot use 2a. If it is a essential singularity, oh, you cannot use 2a or 2b. You have to use Laurent series and find the coefficient of 1 over z, okay? Or 1 over z minus alpha, whatever that is. Okay, good. So here is a function, and I am integrating over this circle. Denominator, cosine z, is 0 at pi over 2 and minus pi over 2. 0 at these 2 points. And it is a simple pole. Or in general, cosine z is 0 at these, right? But we don't care about those infinitely many zeros. We only care about those that are inside this contour. So it will be, by residue theorem, the value of this integral will be 2 pi I residue at pi over 2 plus residue at negative pi over 2. Oh, again, here, because it is a simple pole, I can use 2b, right? Using 2b again. It is a simple pole. I could use 2a or 2b, either one would be fine. So it is numerator, which is sine z, divided by derivative of denominator. Oh, this is -1. So -1 plus -1, that is what you get, right? So that's what you get. Any comment, any question? No question. That takes care of residue theorem. We did have a good review of 16.1, 2, and also 3. For those of you who had already read those 3 sections, I hope you benefited more. And For those of you who didn't have time to read those 3 sections, again, I hope you had a better understanding of those 3 sections. When you read the text, you will learn better. Anyways, go ahead and study hard, please. And as usual, on Thursday, I will upload the test early morning. I'll give you more time. And then you have to return your test with the answers to me by, let's say, 10 o'clock. I will decide on that one, all right? Of course. Yeah, chapter 15, which is sequences series, Taylor series, Laurent series, and we cannot have a test without integration, okay, without Cauchy's theorem and consequences of Cauchy's theorem. So it is not just this one and that one, because we are talking about mathematics, all right? Okay. Any other comment? Good luck, everybody. If you don't have any question or comment, then I'll see you next Tuesday. And next Tuesday, we will talk about clearly yeah, of course, we will talk about the solutions of the test as well, right? Oh, that is Cauchy, this residue theorem was a consequence of Cauchy theorem, right? In the proof or the process that provided residue theorem, we used Cauchy theorem. That's a consequence of Cauchy theorem. Okay. All right. Thank you. Thank you, Del Dodson. Have a good day, everybody. Bye-bye.